In this lesson we see to solve a complete linear system of equations. To be complete, at least one of the independent terms must be different of zero. The normal way of expressing a complete equation system is the one that you have there, in the transparency, where simply appears the coefficients a1 1, a1 2, a1 n, for the first equation multiplied by the unknowns x1, x2, xn, which equals b1, which is one of the independent terms. Evidently, sum of the b's has to be different from 0, for that system to be complete. This is the usual way to see a complete system of equations. How are we working with the orthogonalization algorithm? We have to transform this somehow for us to see where is the orthogonality, and what we will do is the following. First, we are going to create an artificial unknown, which in this case is going to be xn plus 1, since the unknowns are x1, x2, up to xn, and we invent a new one that is xn plus 1. Let's multiply, in the first place, the independent terms the b's, that appear above, by xn plus 1. So, if we do that, we're altering the system, unless xn plus 1 is equal to 1, because if xn plus 1 is equal to 1, we are multiplying the b's by 1, and they are again the same as before. So, let's do both things. Let's multiply by xn plus 1, and force xn plus 1, to be 1, and, finally, let's pass the terms where the b's appear, the other member with changed sign. So, at the bottom, as you see, the system above appears, where the b's have been multiplied by xn plus 1, and they have been passed to the other member with a sign changed. In addition, the new equation xn plus 1 appears equal to 1. What has happened? What has happened is that now the independent terms, except in the equation xn plus 1, equal to 1, they are all null. Then it means that, except the last equation, everything else is a homogeneous system, which also we know how to solve it, because we've seen it then. What are we going to do? Well, look, this transformation, what is saying is, first solve the homogeneous system and, once you have obtained all possible solutions of the homogeneous system, stay alone with those that satisfy the condition that xn plus 1, is equal to 1. In this way, we solve the complete system of equations. Let's see it with an example so you can see how beautiful it is this method. On the top left corner, you have a system of equations, which are 4 equations with 4 unknowns. As you can see there are 4 equations and 4 unknowns, and the independent terms are 1 0 minus 1 0. Since they are not all null, it is indeed a complete system of equations. What are we going to do? As we have 4 unknowns, let's invent a new fictitious unknown, which is x5, that will be equal to 1. Let's not forget of that because you have to impose it at the end. And what are we going to do? We are going to multiply all the independent terms by x5, that is, the minus 1, 0, minus 1, and 0, are multiplied by x5, and moved them to the other member, changing the sign. In this way, we obtain the equation that you have in the upper right corner, which, except for the equation of x5, is a homogeneous system, because now all the independent terms are null. Alright, to solve this homogeneous system, what must we do? We have to get the subspace orthogonal to the subspace generated by the coefficients of the equations. The first equation has by coefficients, for x1 0, because it does not exist, for x2 1, for x3 minus 1, for x4 2, and for x5 1, then the vector which results is 0 1 minus 1 2 1, which we enter in the first column of the algorithm table. We calculate the scalar products, starting from the unit matrix, as you have there, and we see that the first vector has scalar product 0, then you cannot use to pivot, and we use any one of the others. In this case we have chosen the second. So, we pivot, then we enter the coefficients of the second equation. Let's go to the second equation, and we see that the coefficients of x1, x2, x3, x4, and x5 are, respectively, 1 1 1 0 0, and that is the vector that we enter. In this case, we can pivot with the first vector, and that's the chosen pivot. We pivot and we get the matrix in iteration 3. Next we go to the third equation, which has coefficients 1 2 0 1 1, as we see above on the right, and we enter that vector in the third iteration. We pivot, in this case with the fourth vector, and we get the matrix of the fourth iteration, and finally we enter the last equation, which has coefficients 1 1 0 1 0, we pivot and get the final table. What do we have there? We have the orthogonal subspace. You know that you get it by eliminating the columns with which we have pivoted. If we eliminate the 4 columns that we have used to pivot, which are the 4 first, we only keep the vector v5, which is the vector 1 1 0 0 1. The solution of the homogeneous system is what you have there set the right bottom corner, x1 x2 x3 x4 x5, equal to rho times 1 1 0 0 1. Now is when we have to impose the condition that the new unknown x5 is 1. In this case this solution depends on a rho coefficient, and that rho coefficient is equal to x5, then if x5 has to be 1, rho has to be 1 too. Therefore, the final solution that you get by removing the unknown x5, since it was fictitious, is that the vector x1, x2, x3, x4, is 1 1 0 0. This means that this complete system of equations we had at the beginning has a unique solution, and it is that solution that we have found. I must say, that in this process that we have used in the algorithm, we could have eliminated the pivot columns, as we were already using them, so that we would have simplified the calculations, because we would have eliminated some columns. However, we have kept these columns on purpose, because what we are going to do now, require this information. We're going to solve all possible subsystems that result from the given system. We're going to explain in this way. But nevertheless, previously we will clarify how to impose the condition x5 equal to 1. To make it clearer, the solution of the homogeneous system, which we have solved, it's always going to be a linear subspace, which is the orthogonal subspace to the subspace generated by the row coefficients of the equations. This means that the vector x1, x2, x3, x4, x5 will be, in principle, equal to a linear combination of vectors, unless I had no more than the null solution, which would be the null vector. So, it's going to be a linear combination of vectors. In this case, as we have only one vector, because it is rho times that vector, 1 1 0 0 1. If we operate and incorporate the rho to it, we can write the solution as rho, minus rho, 0, 0, rho. So, to impose the condition that x5 is equal to 1, looking here we see that x5 is equal to rho, so if x5 is 1, rho must be also 1, and therefore, the solution that also fulfills that x5 is equal to 1, would be obtained. We let rho equal to 1, and finally, we eliminate the unknown x5, that was fictitious, and we obtain the unique solution of the system that we have mentioned before. Let's see now, to clarify things more, what would we do if we wanted to solve the system formed by the first two equations? If we want to solve the system formed by the first two equations, we have to eliminate the pivot columns that we have used for pivoting with those two equations. Then we have 3 columns left. There we have then that the solution of the homogeneous system x1, x2, x3, x4, x5, is a linear subspace of dimension 3, because they remain three basic vectors. Then three row values appear, which are the ones we use to obtain the linear combinations. We could now group that linear combination in vector form, and see that the first component x1 would be 2 times row 1, plus row 2 times 0, which is 0, plus row 3 times 1, then there is 2 row 1, plus row 3. The second, x2 would be row 1 times minus 1, plus row 2 times 1, plus row 3 times minus 1, then it is minus row 1, plus row 2, minus row 3, and so on. So, if we want to impose the condition x5 equal to 1, we go to the last component, which is the x5, and that is row 3, then x5 is equal to row 3, and since it has to be 1, row 3 must be equal to 1. Therefore, in the previous expression we put row 3 equal to 1, you cannot put any row coefficient, but the value 1. Finally, we have to remove x5, to obtain the final solution of the system formed by the first two equations, to get x1, x2, x3, x4, is equal to row 1 times the vector 2 minus 1 minus 1 0, plus row 2 times the vector 0 1 minus 1 minus 1, plus a concrete vector, which is 1 minus 1 0 0. Which proves that the system has a set of infinite solutions, consisting of a linear space of dimension 2, generated by those first two vectors, and one particular solution, which is the last vector, the same solution that we have used in the case of solving all the equations, since any particular solution of the complete system satisfies any of the other subsystems. Finally, it is interesting to see how this solution we have obtained before, x1, x2, x3, x4, is equal to this vector that depends on row 1 and row 2, which must be real numbers, but are arbitrary. We can put what we want, S and F, it will be satisfied identically. Let's check that by entering these values of x1, x2, x3, x4, in the two equations that you have here, all the terms that incorporate some row values cancel. For example, in the first equation, x2, x3 plus 2x4, x2 is what you have between parentheses, minus row 1, plus row 2, minus 1. As you can see, in the top, minus x3, where we substitute x3 by minus row 1, minus row 2, plus 2x4, where x4 is replaced by minus row 2. If you operate, you will see that row 1 appear twice, once with plus sign and another with minus, and they go, and row 2 appear in three places with plus 1, with minus minus 1, and with minus 2, so that thsy cancel out. Therefore, a value of minus 1 is obtained, regardless of the row values. In the second equation, which is x1 plus x2 plus x3, we simply replace x1 with its value, which is 2 row 1 plus 1, x2 by its value, and x3 by its value. So, when we operate, we see that both the row 1 and the row 2 cancel out and we get 0, regardless of their values. As the same be done with any subsystem of the initial one, with a small additional cost, consisting of operate with pivot columns, although they could be eliminated, you get enough information in the last of the matrices, to be able to solve any subsystem of equations. Therefore, the method that we have explained resolves not only one particular system, but resolves any subsystem of that system. Here you have an example in this table, where four systems appear. The first is the system of all equations, whose solution is unique, and that you have there. The second is the solution of the last equation. So, to get the solution of the last equation, since it's the last one, you have to eliminate the pivot column with which we pivoted, and since it's the last one, we have to delete the W4. Then from the set of vectors that appear above, in green color, we have to eliminate the W4, and we are left 4 vectors, and then how do you impose the condition that x5 equals 1, you see that where there is a 1, in the last row, in the last component, is only in the w5, then that vector will have component 1, and the other arbitrary values. Then, you can see how to solve the last equation, which is a vector space of dimension 3, which are the 3 columns where the w vector appear, and a particular solution, which is the column of v, or v5, where we have removed the last component already, because it corresponds to a fictitious unknown. The same thing can be done with the solution of the last and the penultimate of the equations, for which pivot columns have to be eliminated, and you can see that the solution is a subspace of dimension 2, as you have 2 rows, and a particular solution, which is the same as always. Lastly, in the last element of the table a system appears, where the first, the third, and fourth equations appear. In this case we eliminate the w that have the w1, the w3, and the w4, and what we have left are 2 columns. One is the one that generates the linear space, and another, the particular solution. Then the solution of that system is a linear space of dimension 1, plus the particular solution. I think it's very attractive to check how with a very little effort more, you get that tiny matrix, which is the last of the final table, the one you have up there, in green, which contains all the information needed to solve all the subsystems of equations. Finally, I will show you what is happening when one has a system of equations, which is incompatible. It can happen that the conditions that impose some equations are not compatible with those of others, in the sense that no value of the unknowns satisfy all of them. So, let's see how the algorithm will allow us to detect when this occurs. In this case we explain it with the help of an example. Here is an example which is the system of equations at the top left corner. 385. They are 4 equations with 4 unknowns. In this case, since there are 4 unknowns, we use a new artificial one, x5, which will be equal to 1, and we will multiply it by the independent terms, and will pass them to the other member changed sign, to get the system you have at the top right corner. If we want to solve this system, we know that we will get the subspace orthogonal to the space generated by the vectors of the coefficients. So, we start by entering the coefficients of the first equation, which are 0, 1, minus 1, 2, 1, that you have there. We pivot with the second column. We go to the second equation. The coefficients of x1, x2, x3, x4 and x5 are 1, 1, 1, 0, 0, because we have neither x4, nor x5, and we pivot without no problem. We go to the third equation, which is the one that has coefficients 1, 2, 0, 2, 0, and we enter it. We find the following: with the columns 1 and 2 we cannot pivot, because we have already pivoted and they are vectors w, instead of vectors v. So, we have 3 more vectors v, 2 of them have null scalar product, and cannot be used, what forces us to pivot with column v5. This is a very clear indication that the system is incompatible, and I'm going to try to explain why. If we pivot with the v5 column, what will happen? Well, if we pivot with v5, it will not be in the final solution, because that vector v5 will become a w5, that is, it will no longer be able to be used as pivot. So it means that as that column becomes a w column we will have to remove it from the orthogonal linear space generators at the end when we find the solutions, before forcing the condition x5 equal to 1. Thus, that column will be removed. So, we will be left alone, the columns with headings v3 and v4, but unfortunately these columns in their last components they have 0, which means that no linear combination of vectors that have the last component 0, will produce x5 equal to 1, then there will be no solution. So I want to indicate that what is interesting about this algorithm, is that apart from solving a system of equations, it gives us the solution of all the possible subsystems and also allows us to identify in a clear way when it is incompatible and the equation that produces this incompatibility, which is the equation that forces the pivoting with the last column. If it forces us to pivot with the last column, at that moment we stop, and we can say that the system is incompatible and this equation is incompatible with the previous ones.
Si nos fuerza a pivotar con la última columna, en ese momento paramos y decimos el sistema es incompatible y esta ecuación es